Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you for coming to the second session. And we have very nice 4 talks today. But I have one quick announcement from the organizers. If you present games, then please bring your laptop during the coffee break and also lunch break. Please bring your laptop and then demonstrate your game near the poster session so that people can try your game. So today and tomorrow, please bring your laptop and demonstrate your game, please. And the first talk will be given by Ulrich Brandes. Thank you.
All right, now you should hear me better. This is joint work with my PhD student, Mirza Klimenta. And Peter Eads calls it a myth that professors are important. This is based on the conjecture that there's an exponential decay in knowledge compared to the next generation of students that you have. And Mirza is my PhD student. He should be 5 times more knowledgeable than me, according to this conjecture. And maybe here's some evidence to support the conjecture. These are the last 3 theses, PhD theses, that I had to review. This is Mirza's that he just turned in. It's the most comprehensive work on MDS for graph drawing that I have seen so far. And just to be sure, it's 11 points with small margins, right? So he should really be giving the talk, but it was too difficult for him to get here, so I will do that. It's about MDS, and MDS, I just briefly recall what the principle is. Given some pairwise dissimilarities between objects, we're trying to represent them in some geometric space, 2 or 3 dimensional, such that the distances in that space resemble the dissimilarities that were input into the method. It's a whole family of possible approaches, and the 2 main variants are shown here, or are illustrated here. In GD, the typical use of this method is that the dissimilarities that we input into the method are the shortest path distances in the graph, but other distances are possible. Right? And of course, the target space is 2 or 3 dimensional because we would like to look at these drawings at some point. The 2 main members of this family, or the main distinction between different members of this family, is between classical scaling and distance scaling, where classical scaling was the first method proposed in this respect. This is based on spectral decomposition, so it's basically a spectral method, and this one is an iterative method that tries to optimize some objective. You can see that there's a qualitative difference between the results. Qualitative not in terms of quality, but in terms of they're really distinct, the kind of results that we obtain. Local details are much better visible in this case, whereas large distances are represented very well in this case, with some degeneracies. Right? This is the comparison between the 2. As I said, one of them is based on spectral decomposition. The other one is based on iterative minimization of a quadratic objective. For the spectral decomposition method, one of the good things is that we have very fast approximation methods. For distance scaling, this is not so much the case, even though there are speed-up heuristics. There are, because it's a spectral method, if the spectrum is not well behaved, if we have multiple or higher multiplicity of the large eigenvalues, there can be degeneracies. And you've seen some of those degeneracies as well, because we're only representing a subspace. For distance scaling, we have local minima. Because of the iterative method, it highly depends on the initialization, and you've seen examples in the previous session that this may be the case. Because this is spectral decomposition, it's also considered to be very inflexible, because we set up a matrix and then we look at the eigenvectors, and there's nothing we can do about the result anymore. Whereas here we can fiddle with the objective function, we can change weights, we can introduce other elements into the graph and so on. So it's considered to be more flexible. In terms of the result, the overall qualitative difference is that we see very well the overall shape of the graph in this case, because of this tendency to represent larger distances more accurately, and we see more of the local details of a graph in the distance scaling method. So the conclusion of this comparison is that in practice, the typical way of using this is to use classical scaling as an initializer to unfold the graph very well and then improve the local details by running a few iterations of distance scaling. So as a simple way of memorizing this, C is before D, right? What I'm going to do in this paper, what I'm trying to show is that we propose two adaptations that address the inflexibility and the degeneracies of classical scaling. Because it is such a fast, can be approximated so fast, we can apply this to very large graphs. But if we look at very large graphs, we still want them to look decent. So we show that there are ways to modify classical scaling in such a way that we can control the output a little better than maybe if we apply it in the standard way. Because it's about classical scaling, just in a nutshell, what is the spectral decomposition method? Our input are some dissimilarities. Typically, they would be metric, but in graph drawing, they are because we are using shortest path distances. The goal is to find coordinates represented as an n by d matrix, where we have d-dimensional coordinates represented as row vectors, such that the input dissimilarities, the shortest path distances, are represented well by the Euclidean distance in that target space. Right? And note that distances are closely related to inner products because we can represent the square of the distance as a sum of some inner products. Right? So we can look at classical scaling as the reverse or as a reconstruction task, because if we knew the coordinates, we could compute all the inner products. From the inner products, we compute the distances, and then we have the matrix that was given as the input. Now we're trying to do the reverse, not knowing even the existence of such coordinates. So we set up an inner product matrix using this formula, which is derived from the other, or easy to recognize formula, in such a way that one of the degrees of freedom is resolved. Because distances, of course, are translation invariant, whereas the coordinates are not. And the way that this degree of freedom is resolved has an effect on how this is set up. In this case, it's the centroid of the configuration that is placed in the origin of the result. Right? It's not, the details are not that important. It's just just important to see that we can easily set up this matrix by doing some computations on the input dissimilarities. And then we apply a standard method of decomposition. So this matrix is symmetric. We can do spectral decomposition on this matrix and get the coordinates out of this. Right? So this is what we do. We get the matrix of eigenvectors of B, the diagonal matrix of eigenvalues, and again the eigenvectors. And then we cut this in the middle by just taking the square root of the eigenvalues here for the d largest eigenvalues that we use as the dimension of the result. Right? So not difficult technically. Two things to notice is that it is known that this decomposition is the best rank D approximation of the original matrix B. So what we're basically doing is we're optimizing an objective function that looks like this, where the error in the inner product is penalized. Right? So we're trying to optimize this function implicitly. And because of that, we have a bias towards larger distances. This is where this comes from. All right, so this degree of freedom of choosing the centroid as the origin is very important for what we're doing. So let us look at this more closely. It has been noted many times in the MDS literature, but it has not been used for graph drawing so far. So let me just characterize it a little bit. If we have input coordinates of the same dimensionality that we're trying to reconstruct, so we're doing a full reconstruction, and changing the origin, resolving this degree of freedom in a different way corresponds to a rigid transformation. So we're just shifting the image around. If we do low-dimensional construction, because the input may not be metric at all, then this results in a distortion. Right? If we pick any particular vertex of the graph as the origin, we can set up the inner product matrix in this way, which looks almost like the previous one, because the previous one was the average of all vertex coordinates, and now it's only one particular one. So in general, we can weight all of the vertices in any way. So any convex combination of the other vertex positions can be chosen as the origin. And all that needs to be done is to set up the inner product matrix in a slightly different way. So we're not changing complexity and so on. We're just choosing where we would like the origin to be. And the effect is seen here. So this is the centroid of the configuration and the standard classical multidimensional scaling solution that you would get. If we pick, for example, this vertex, the result is slightly different, right? Because we're reconstructing different inner products. And if we pick, for example, the graph center, so the average of all of the vertices in the center of the graph, the vertices with lowest eccentricity, then the result would look like Batman, right? All right, so we can control a little bit of the shape by focusing on one particular area. And this is what the first contribution is, that we're suggesting a method to do focus on context within the framework of classical scaling. Right? And the approach is fairly simple. The goal of the focus on context technique is to enlarge some area, to have a more detailed view of something that is too large to be represented on the screen entirely. So we focus on one area, but we would like to preserve the context enough to orient the user in the graph. Right? This is the main idea. What we do here is we set the origin of the configuration to the focal point that we would like to address. And then we change the way that the inner products are being set up. And we change them in such a way that, you have seen before, that the inner products are now expressed in terms of some particular origin. We just control the contribution of the length of the distance from that origin, and we control the angle between the two position vectors. So what this does is that we can enlarge an area by choosing R appropriately, right? Focus on all of the distances that are close to the focal area, and we can also spread the context around by changing the exponent for the angle. In comparison to previous methods, for example, for fisheye views of graphs, which are very typical, this is an input space method. We're changing the data that is input into the algorithm rather than what is usually done an output space method, where the distortion that the method introduces is already there, and then it is additionally distorted. Right? So one thing to notice about this particular fisheye method is that the context is fairly narrow, because we're enlarging some area and the rest shrinks. But by controlling Q, we can enlarge the context or use the empty space around the context to show more of it in the same drawing. Right? So it's one way to control this. And I think one of the good things about it is that the distortion is happening only when the method is applied, and we do not have these uncontrolled interferences between the two distortions that are introduced into the drawing. Because we have these two parameters, we can use them differently. So for the same graph, we can put the focus here where the color indicates how much the edges are distorted, or we can put the focus here. So that's just a change of origin to show that we can actually enlarge different areas. But now if we change the parameters a little bit, we see that in this case, the focal region is enlarged and the context is slightly shrunk. Right? By just changing the parameters in this way. And of course, the graph has been chosen because things are easily observable in this particular graph. We can apply this also to bad layouts, and the same thing happens. But of course, because the layout as such is bad in the beginning, the focus and context does not look that good on this graph as well. Right? So it's not a good demonstration, but it shows that putting a focus here, putting a focus there, putting a focus there has the same effect on any kind of layout. Sasha?
The reason why you chose R and Q the same?
No. Just for illustration. It can be anything between 0 and 1, and here we see that when we choose them, oh no, we didn't even choose them different. Oh yeah, here it is different. Right? It should be independent controls, but maybe I didn't demonstrate it enough. All right, so that's one thing. Because classical scaling can be approximated very fast, this is an interactive method. So I claim that the layout usually takes less time than rendering the graph. So we can do this in an interactive setting where we change the two parameters or where we change the focus to our liking. The second, no, not the second, the addition to this first method is that maybe we have multiple foci that we would like to look at. And using the same type of projector that we used for picking one of the origins, we can also pick different focal regions and then combine the results. Right? So we do a weighted combination of all of the inner products. Then we have to pick a common origin or a common focus for all of them, which will affect the results. But what you can see is that one focus here, one focus there, and if we combine them, then we get these two enlarged areas as well. Right? But here it is a matter of where we choose the common origin, what the actual results will be because of that translation variance of the inner products. All right. Now the second modification, I think, is the more important one. So this one is practically more relevant. I think this is the one that's coming now is more important for the quality of the results. If we consider classical scaling as a reconstruction task, then there are actual coordinates, and we can rewrite the way that the coordinates are produced into something that resembles more a projection. This is actually known as principal component analysis, but I'm summarizing what it does. We have the original coordinates, and these coordinates are transformed by equalizing the spread along the dimensions and orthogonalizing them. Right? Never mind, these are the eigenvectors of the inner product matrix of the coordinates. Using this, we get some projection that has this effect. It can be shown that this is the maximization of the distances between points. Right? So we're spreading out the drawing in all directions as much as we can. This is what would happen if we knew the coordinates. Now what we're going to change is this projection matrix. Right? Because the deficit of classical scaling really is that if we have these high-dimensional coordinates, to maximize this term, it is greedily selecting the dimensions. This is what is the most important thing in these data transformation operations, that we would like to maximize the variance along the dimensions, but for the drawing, this may be very bad. So here, the first dimension that is picked is the long version through the graph, and then the second dimension is the second longest axis, basically, that we can find in this drawing. So this is the result, even though the three-dimensional configuration that defined the input is not very well visible in this type of projection. Right? So what we'd really like to see is most of the graph. And how can we do this? Well, we change the objective to a weighted version of the original objective by modifying the projection matrix. So instead of the eigenvectors of the inner product of the coordinates, we're using a weighted version of this, where this is the Laplacian of some weighting scheme that I'm not going to detail out. So this has been observed by Yehuda Koren and Kamel and explained in detail, but we're just using it here to improve the projection that we get for the original coordinates. And this is the result if we just take the adjacency matrix as the weighting scheme, compute the Laplacian out of this, and then enter this into the eigenvector computation, then this is what we actually see of this three-dimensional projection. Because we're now maximizing the length of the edges in the graph. Right? The weights filter out all of those pairs that are not connected. So now we're not connecting, maximizing all the distances, but only those distances between nodes that are adjacent. This is why we see more of the edges in this projection. Now in our case, coordinates are not known in the beginning. Right? The more dimensions we have in classical scaling, the better the representation is. So our new technique here is to start from the dissimilarity matrix to do classical scaling, but in higher dimensions than we actually have as a target. To have more of the details represented in this higher dimensional space, but because most of us are not capable of looking at 10-dimensional drawings, we then apply weighted PCA to get to a good projection of this drawing. So we choose some h, for example, based on where the eigengap is, where most of the data is already represented, and then we do this type of projection, for example, in the same way that I showed before, but to be sure that we're not looking from a very bad direction that has lots of occlusions, we're adding a few random diodes to stabilize the projection with respect to what we would normally get. Right? So just a few of those. And it can be shown, and that's in the paper, that this is again related to the choice of origin. The choice of origin can be expressed in this framework as well. And this is the final slide showing just one example. This is a typical 2D classical scaling of one of the matrix market examples. This is what we get when we do this in 6 dimensions to represent more of the details in that higher dimensional drawing. And once we have the coordinates, we choose a perspective that shows most of the graph. And even though this may look very fuzzy, it actually shows in this detailed view that we have all the differences between those nodes that would not be visible in the two-dimensional projection because they're only represented in higher dimensions. Right? This is a node that has 500,000 edges, the graph that has 500,000 edges, using the basically linear time approximation algorithm for classical scaling. This is done in seconds on a regular laptop computer. Right? That's all I had to say. Thank you.
For Ulrich, Peter?
Can you say anything about interactivity, say in the focus plus context thing? Can you make a smooth transition from one focus to another focus by adjusting the weights? Is it possible? It looked like it's possible, but
So I haven't thought about it, but I think so. I think it's a good suggestion that we change the weighting scheme for the unit vector that focuses on one vertex to the unit vector that focuses on the other by just interpolating between them.
Seems by just adjusting those two parameters.
Yeah. Well, not the two parameters, but the choice of origin. So if we move the origin from one node to the other.
Not the origin, no? Oh, no, you can move it geometrically, right?
Yeah, in input space.
Okay, Ben.
That was a terrific presentation. Appreciate it. I have two concerns about. One is the fisheye representation. In the examples you show, the zoom factor is only about 2 or 3, and most studies show that the spatial instability is damaging, and that the advantage only comes when you get 5 or more. So, have you gotten examples where the focus versus context has a zoom factor of at least 5, and that really shows a value to the tool?
No, it's a very good point. We basically wanted to demonstrate that this method is more flexible than it seems to be, but of course that should be explored.
Fisheye or magnification approaches or distortion-based approaches are undermined by the lack of spatial stability. So that was a concern. The other about the multidimensional scaling, I'm still not convinced that it provides an effective representation because the parts of the graph where the representation is weak are not emphasized. So we don't know where to trust it and where to doubt it. Is there a way you see of solving that problem to make MDS a better payoff?
So I think that CS is really, it's good at representing these finite element meshes because they have some geometric origin to them. If it's a graph like in the beginning, we still would like to use this as the initialization. But if the initialization is better, then the distance scaling will work better as well. The representation error is something that we thought about representing graphically, for example, by coloring and so on. But we don't know yet whether.
Try another idea which maybe you've thought of or have a solution for, which is, can you characterize a family of graphs for which MDS provides effective representations?
Yeah, that depends on the spectrum.
Okay, so David.
Okay, thank you.
So this relates to something you said at the start of the talk, and then again just now, that you say we should be doing CS and then DS. When you try it with this method, does the DS undo some of the differences that your weighting makes? Or is there a way to make your choice of weights for the CS part to carry those weights over into the DS phase of the algorithm?
I'm not sure whether it's easy to control what's happening. I would think that we could limit the displacement that DS is actually doing in the end, and maybe we could also change the weights in the DS, but that's something that needs to be explored.
Stephen?
Why 6?
Oh, because that's where the eigengap was largest. So any additional dimension would not have added much more detail.
So in general, you can look at the eigengap and choose to go to 20 or 7 or 17.
Yes.
Cool.
Okay, thanks for Ulrich for giving nice presentation. And the second talk will be given by Lowell. And the title of the talk is Force-Directed Graph Drawing Using Social Gravity and Scaling.
So, yeah, they got me set up already. So this was work done with Michael Bannister, David Eppstein, and Michael Goodrich. Get started here. So just a brief outline. We're going to cover a little bit of background, briefly on force-directed methods, because we've been talking about that a little bit earlier. what we mean by social gravity, what we mean by scaling, and then we'll look at some examples in trees and drawings of social networks with a brief foray into some things that concern Lombardi. So quickly, what are force-directed methods? We'll also refer to as spring embedders. They're a method for drawing algorithm, or an algorithmic method for drawing graphs that are fairly flexible. And a nice feature is that they require no domain knowledge about the graphs being input. The model we're basing our algorithm off uses primarily two simple forces, a repulsive force between all nodes and attractive forces between adjacent nodes. So some of the challenges that these methods face is that modeling a physical system tends to have local minima that you can get trapped in and not produce the optimal drawing that you'd prefer. And modifying the sort of simple forces by adding additional forces can make it even harder to get out of these local minima. So what are we going to do? Let's add more forces. See what happens. Social gravity is the force we're going to be adding to the simple set. The way this breaks down is the force vector on a particular node is made up of a gravitational constant that we'll talk about in a second, the mass of a node, which we'll actually use social metrics to define, and then that node's relative position in relationship to the center of mass of the graph. So what do we mean by mass in terms of a social metric? Well, we're going to use something called centrality to define which nodes are important. Centrality is a metric used in social network analysis to give some understanding of nodes, or rather the entities they represent in a social sphere, importance based on their structure, their location in the graph structure. So there's a few different definitions. We'll get into them here that we'll be referring through. One is degree centrality, so pretty straightforward. Node's degree centrality scales with its degree. The idea being that if a node is higher degree in maybe a social context, it's more likely to get infected by an infection traveling in the network just because it's more connected. Closeness centrality, it's just a measure of how close a node is to all other nodes in the network. So it's the inverse of the mean distance from a node to all other nodes. And as you can see in the drawing to the right, as a node kind of feels more central, you'll see the closest centrality raise. Our heat map kind of goes from lower, cooler colors to brighter reds. That'll be important later. And then finally, betweenness centrality, which is just a summation of the fraction of shortest paths going through a particular node. So the idea being that if you're a single node, you consider all shortest paths between pairs of other nodes in your graph, and then some number of shortest paths between those nodes will pass through you and some will not. So your fractional importance is the number of those that do pass through you over the total number of shortest paths. And then you just sum that over all possible pairs in the graph. And as you can see in the example to the right, the centrality of the top two nodes is lighter than the centrality of the bottom center node because the shortest paths between pairs from the left to right are split between, or the possible shortest paths are split between those nodes, whereas in the bottom example, they're not. All right, so what do we mean by scaling? This is important. The idea is that we could, from the onset of our algorithm, just input the gravitational force as a constant value and run the algorithm. So if we look at a simple forest here, laid out with a classic inverse square spring embedder, you'll see that it has begun to separate a little bit. Now, if we add a gravitational force, and you'll have to, this is where I need audience imagination. These slides are PDF now, so they don't actually animate anymore. But that graph over to the right that is obscured will slide over to the center. Now you can see this graph, the subcomponents of the force have been pulled together using gravitational forces. Now, this was done with a gravitational force that was consistently high throughout the layout of the algorithm. And you'll see that it's a pretty decent drawing. We don't have any crossings. The subcomponents are closer together, maybe easier to view. And then in the next drawing, we'll see that this is a drawing where the gravitational forces were scaled up. So gravitation started at a very low value and increased over time until we achieved a drawing that we thought was acceptable. And then if we compare the two, you'll see that there's not many differences here. So this is actually kind of a counterexample to what I'm about to tell you, but it works pretty well in the small case. The gravity seems to not affect what we're doing, how that gravity is increased. But if we look at this example, a little bit of a larger forest, we'll see that there are actually a lot of crossings. 1, 2, maybe 16. But this forest, because it's a little bigger and a little more complicated, wasn't able to cleanly break from itself before we began a gravitational layout. So in the next case, you can see the same forest where gravity started out low and slowly increased until the final drawing was achieved. And here we get a lot cleaner of a visualization. So there is actually one crossing in there. I'm not going to tell you where it is. You have to find it for yourself. So how do we do our scaling? Well, we have this very complicated diagram here. Not really, because what we found in our algorithmic study is that how we tweaked our scaling wasn't really as much important as that we did increase from a lower value to a higher value. So we used a simple step function. A few iterations increase gravity, a few iterations increase gravity, and so on until we achieved something we thought was a nice drawing. What we found is that varying the number of iterations before gravitational increase or the size of that gravitational increase didn't actually modify our results too much. Obviously, there's some work here to see the effects of maybe a more complicated function on the final layout. And so now we'll look at some examples in terms of trees. So here's a tree drawn with closeness centrality coloring. So the red nodes, as you might imagine, have a higher closeness centrality value. And what you'll see drawn with a classic spring embedder, this tree kind of spreads out. And some of the connections at the edges might be harder to determine cleanly. You get a kind of less angular resolution out at the extremities. But when we draw this with a little bit of gravity, what we see is that our total area coverage per node is decreased. So a higher node density and a better distribution, or a more uniform distribution of nodes. Now you do kind of sacrifice some of the, I guess, immediate contextual notion of where nodes are in the tree. But if you pay close attention, you can see that there are no crossings, and the separate tree paths still remain fairly separate, and our higher centrality nodes, because of that gravitational constant, are pulled towards the center. So here we have a convenient coloring, but if you were labeling these nodes with something else, not centrality, the nodes that you might prefer to learn about in a social context, those with high centrality based on your decision of which metric, are in the center of the graph. So those would be probably viewed more aptly by someone trying to examine the data. So here's another tree. And we can look at this tree drawn as well. And there would be some nice animations here, but imagine trees sliding in. This is the same tree drawn with a few different types of centrality. So up in the left here is degree centrality. This is closeness, and the far right is betweeness centrality. So this is just to illustrate that although the centralities are somewhat related, they do differ, but the structure is generally the same for these simple trees. Because centralities share some notion, the structure of the final drawing tends to be similar. Now, here's an example of a much larger forest with a few interesting pieces. The larger trees of the forest are drawn towards the center because they contain nodes with higher gravitational masses. And you still get, despite the number of nodes and connections, crossing-free drawing. So moving on to actual social networks, here's just a few examples. On the left, you'll see a social network that kind of looks like a traditional drawing. Maybe the nodes that have long edge connections out are further away from the center than you might hope based on their centrality value. On the right, as you can see, those nodes are drawn in towards the center, and a definite increase in angular resolution on the extremities. Here's another tree drawn with closeness centrality, and finally one with betweenness centrality. And as you can see, the increase in uniform node distribution really helps in sort of distinguishing which nodes are connected. You kind of lose that in this region, but you're able to understand that a little better on the right. So not to bum everyone out, but we're going to look at a few more real-world social networks. So this is an infection graph with closeness centrality, and one more with betweenness centrality coloring. So even as the nodes get more complicated, or the graphs get more complicated, we still gain in angular resolution and a little bit of understanding of local node placement. So a brief foray into Lombardi. So hopefully those of you who were here last year heard all about who Mark Lombardi is. He's an artist who drew by hand conspiracy networks with long long arc edges. So on the left here we have an example of his work, and on the right a straight line approximation of that drawing. And then so if we slide this over, we can see that same graph drawn with our algorithm. Now while we don't maintain the same node placement that Lombardi used when he hand constructed this, we do gain some movement of the high centrality nodes towards the center. These, I don't know if I said, are conspiracy networks. So you might actually want to know that the nodes more central to the conspiracy would be located at the center of your network. And then here's another example. And on the right, that drawn with our algorithm. And then because this is a force-directed method, you can actually use one of the results from last year to do a force-directed Lombardi drawing to augment the forces used and add curvature to the edges. So on the right, you'll see some long curved paths that you would hope to get from those results. So our gravitational force actually works seemingly well with the Lombardi force. So now let's take a brief look at our algorithms in action. So if I can full screen this. So here you see a tree being laid out. And as the gravitational force increases, you'll see those extremities spread and be drawn towards the center. And the nodes reach a more uniform distribution. And obviously, if gravity gets too high, you may have caught it there, you get one crossing. So there is some limit to how high you can take gravity before your drawing starts to degrade. Here's a small social network. And so the pulsing that you see happening is actually the scale of the drawing increasing. So as the gravity pulls the nodes together, and the bounding box shrinks, we're blowing the drawing up. So just to maintain visibility. But when you think of relative position, you still get the benefits we're looking for. And here's a forest. So here in the forest, you'll see that the standard forces actually repel the subtrees. This is where that scaling becomes really helpful. So this allows some of those crossings that would get caught up to kind of cleanly be eliminated. And then the gravity begins to draw the subtrees back in until you get the drawing that you're going for. All right, great. That's all I have. Thank you very much.
Do you have questions, Ulrich?
Do you have a way to control whether the subtree or the trees of the forest overlapped in the end? Because it looked like they were repelling each other.
Yeah. So they're repelling each other with the standard repulsive forces. One thing that we didn't get into too much is balancing those repulsive forces with the gravitational forces. We kept the gravitational forces fairly light in comparison because we thought that the traditional methods seemed to construct really nice graphs on a regular basis. So we didn't want to overshadow that with a really intense gravitational force. But yeah, if you want the kind of intermingling, you can reduce that initial scaling period. So have a stronger gravitational force at the beginning.
Other questions?
Yes, so in your case you always get circular outlines in the end. Since most computer screens and pieces of paper are rectangular, is there a way to define gravity in a way that you would get something rectangular?
You know, we thought about that. I don't actually remember how the, yeah, maybe.
So we actually tried using like an L1 metric or something like that instead of a normal Euclidean metric under the hopes that it would, it just produced chaotic. But I think it would be very simple, and I didn't try this one yet, but to simply get oval shapes so that you could maybe fit a widescreen monitor better by scaling one of the components of the Euclidean metric. That should work. I don't see why not. Yeah. To get squares. Okay.
So you said at the beginning that in exchange for getting this better angular resolution and more even node density, you lose some of the immediacy of being able to see the overall structure of the graph. Have you done any studies to see do the benefits of this actually outweigh the costs in terms of actual readability?
No, we haven't. But I would love to see the results of those studies.
More questions? Okay, let's thank to Robert again for the nice presentation.
The rectangular filling is really, have you thought about the repulsive forces at the borders?
And the title of the third talk is Progress on Partial Edge Drawing. And the talk will be given by Tim.
Almost like a prefab rectangular.
So I'm going to talk about progress on partial edge drawing. It's a joint work with Sabine Cornelsen, Carsten Gutwenger, Michael Kaufmann, Fabrizio Montecchiani, Martin llenburg, and Alexander Wolff. So first of all, what is a partial edge drawing? Consider an arbitrary graph with visual clutter caused by many edge crossings. And one of the main questions in graph drawing is to reduce the number of crossings. The traditional way is to simply change the embedding, but what we do is we break the edges, so every edge becomes two pieces, which we call stubs, and now we shrink the size of these stubs. So if we remove the middle half of every edge, we get a layout with only 23 crossings compared to the over 400 crossings before. We can even reduce the number of crossings to 0, and yeah. This is a layout showing that. The motivation for this is a talk from last year given by Bruch et al. He evaluated partially drawn links for directed graph edges and considered two layouts for edges, the taped and traditional drawings of edges, and considered variants of length of these stubs. And he wanted to know if such a drawing makes it more clear to understand the graph. For example, with the question, is there a path of length 2 connecting the red and the green node? And the users of the studies must click some buttons, yes or no, and so on. And the result was that for this question, when we shrink the size of the stubs, the error rate increased. But if we consider another question like pointing out the node with the highest out degree, then we can see with a lower stub size, the error rate decreases. So, and this is very interesting because at the length of 75%, there is a dip, so that motivated us to introduce a formal definition for partial edge drawing. So what we do now is partial edge drawing is defined as a drawing where every edge is replaced by two stubs incident to the start and the end vertex, and the stubs are not allowed to cross. So if you ask now which graphs admit such a drawing, the answer is any graph, because you can draw the stubs sufficiently small. To make the question more challenging, we introduce further properties. Consider the complete graph with 6 vertices. Then we can introduce a symmetry. That means both stubs of every edge have the same length. And we can introduce homogeneity. That means the ratio of a stub to its edge length is the same over all the edges. In this case, we removed the third quarter of every edge. And of course, we can combine both properties to a symmetric homogeneous partial edge drawing. This is an interesting drawing because if the ratio of a stub to the edge length is known, then you can guess from the length of the stub and the ratio where the corresponding end vertex is. And so we consider those drawings with a given ratio. In this case, we have the ratio of a quarter. That means one stub is a quarter of the total edge length. And we also consider the case of symmetric partial edge drawings, where we maximize the sum of the stubs. So what I'm talking about is, first we show that a quarter SPAD does not exist for a complete graph with more than 212 vertices. Second, I show some existences of delta symmetric homogeneous partial edge drawings for some classes of graphs. And finally, we consider the minimum SPAD, which has two approximations. A minimum SPAD corresponds to the maximum SPAD if you minimize the gaps instead of maximizing the stubs. Okay, first of all, we require no embedding and fix the ratio to a quarter to make it more easier. Then there is a result from a previous work that the complete graph with at most 16 vertices admits such a quarter SPAD. And a drawing of this looks like this, as you see on the left side. And it seems to be impossible to add a further vertex in this drawing without any crossings. But what we can only prove is that for 212 vertices, it is not possible to draw a quarter SPAD. Our first idea was we consider a point set with 30, choose 15 points, and Erdo-Sikares says that then we have 17 points on a half-sided convex hull. And for those points, we can easily show with the following techniques that such a drawing does not exist, but the number of points is very huge. So we reduce the number with taking a closer look to the point set. So if you consider an arbitrary point set, we choose 2 points with a maximum distance and rotate the point set so that this line, connecting line, is horizontal. And we arise a rectangle enclosing all the points, and now we consider just the top part of this rectangle. Here we have 3 points, the left, right, and top point, having stubs, and they define a partition of this rectangle with the property that every point in such a cell has 3 stubs crossing the cell boundary. And now we compute for every cell of these 26 cells how many points fit in these cells. And as an example, we consider the red sign cell, where we have 1 point, at most 1 point, with the property that it has 3 stubs crossing 3 different segments of the boundary. Any further point has 2 stubs crossing 1 single segment of the boundary. And from the slope of the top stub of the lower point and the size of the stub, the left stub of the upper point, we can compute that there are only 2 points possible in this cell. And so we do for all the cells and get a total number of 107 points in the top part of the rectangle. Now if we double this number and take into account that the left and the right point are counted twice, we get this number of 212 points. Okay, now we come to the existence of a delta spread for some classes of graphs, and the key concept is that we enclose every vertex and its incident stubs by a circle, and if we know that the circles don't intersect, we know the stubs do not intersect. Although there might be drawings where circles do intersect, but the stubs don't intersect. So if we consider some vertices with a certain distance of two connected vertices, we see that one unit of distance covers 2 times the radius of such a circle. So we can compute from the distance the ratio of a stub so that it is contained in the circle. And in this case, for a distance d, we have 1/2d as the ratio. If we consider now graphs with bandwidth k, that are graphs where we can order the vertices along a line, and if there are vertices connected, the distance of these vertices is at most k, then we are sure that there is a 1/2 square root of 2k spread, in that way that we arrange the vertices in a snake-like fashion and compute the maximum distance. And this is square root of 2k in this case. And by our first consideration with the key concept, we can find this square root of 2k in the ratio of the spread. Now for k-circulant graphs, we can do similar considerations. K-circulant graphs are graphs where we can order the vertices on the boundary of the circle, and every vertex is connected to at most k left or right vertices. So we take the same snake-like fashion and draw it on an annulus, and if we compute the distance, we get again a value of 4 square root of k. Replacing it in the key concept formula, we can prove this. Now we can change the concept. Instead of circles, we can consider rectangles and ensure that they don't overlap. For considering bipartite graphs, we consider just one set of vertices, which we place side by side, and can compute from the ratio the number of vertices in the row. And we can also compute the number of vertices if we place the vertices of one set on top, in the way that if we have placed one vertex, the other one is upper bound by the value of 1 minus delta, and we can iterate this to the lower bound of delta. So if we see in the next formulas a value of 1 over delta, we know there's a side-by-side placement of vertices, and if there is a value with logarithms, we know there is a top-on-top placement of vertices. So if we consider now the complete bipartite graph with 2k plus n vertices, we see there is a bound for k with a logarithm, so there is a top-on-top placement for the construction, as you see in the top and the bottom of this construction. And the remaining n vertices are placed on a horizontal line. In this case, if we have a ratio of a quarter, then this k is bounded by 4.8. And we can also consider the complete bipartite graph with 2n vertices, and there both of the factors appear. So that means we have a side-by-side placement in the column and a top-on-top placement of the columns looking in the horizontal direction, and both on each side of this drawing. Now, to have no overlappings of the edges, we move some of the vertices slightly. Now we come to the minimum spread, which has a 2 approximation. First, we change the concept in that way that we require neural embedding, so that we have fixed vertex positions, and such graphs are called geometrically embedded graphs. And for maximum spreads, for geometrically embedded graphs, we know there is a it can be computed by dynamic programming in n log n time if the graph is two-planar and is NP hard to compute in general. So we consider now the minimum SPAD, and here we get a 2 approximation of m to the 4 time, where the approximation is quadratic in the number of crossings, and the crossings is quadratic in the number of edges. As I said before, the min SPAD is if we minimize the gaps of a drawing, and therefore we show that a transformation from the min SPAD to the minimum weighted 2 set. And what we already know is that this problem has a 2 approximation. Okay, what we do here is we consider an arbitrary edge and the crossing edges as denoted by F1 to F3. And we order the crossing edges Fi according to the distance to the closest endpoint of the edge. And the pair of segments Ei are now the part from, for example, from this vertex to F2, if we define the one part of the segments per E1. So Ei in general is defined by the I+1's crossing edge. And those segments create now variables in the instance of our problem. And we say that the pair of segments is not drawn if the variable in the instance is true. Then we have to introduce the implication that if we've drawn segment Ei+1, the segment Ei must be drawn too. And of course, for every crossing, we introduce another clause. Not both of the segments will be drawn for each crossing. For every variable, now we introduce a weight, Vei, and we get now the instance, the problem of minimizing the weighted sum of the variables for overall the valid variable assignments. This is a quite interesting thing, but what has it to do with the max SPAD? For exact solutions, min SPAD is equal to the max SPAD. But to get a 2 approximation for the max SPAD, we would need a transformation to the maximum weighted 2-set problem. This would also solve the maximum independent set problem, and this has no 2 approximation as far as I know, and so it is unlikely that the max SPAD has a 2 approximation. So let me conclude now the results. We have proven that there is no quarter SPAD for the complete graph with more than 212 vertices. We found some classes emitting a delta SPAD, and computing maximum SPAD is NP hard in general, and the min SPAD can be 2 approximated. For the future, we want to find more classes of graphs admitting a delta SPAD, and we want to close the gap between 16 and 212 vertices. As we saw in the picture of one of the first slides, it might be possible to improve the bound to 17, but it seems to be very, very hard. And of course, we want to generalize this concept, not to have a ratio of a quarter, but a general ratio. Okay, that's it.
Any questions for Till? Okay, so let's thanks to Till again. Thank you. So title of the last talk of this session is Implementing Partition 2-Page Book Embedding Testing Algorithm. And Marco will give a talk.
What is it? Okay.
Good morning. My name is Marco Di Bartolomeo, and this presentation, I'm from Roma Tre University, and this presentation is a joint work with Patrizio Angelini and Giuseppe Di Battista. A two-page book embedding is a type of graph embedding where the nodes are aligned along a line called the spine, and the edges are assigned to two half-planes sharing the spine called the pages. Everything is done in such a way that in each page the edges do not cross. In the partitioned two-page book embedding of a graph, the problem for a graph consists of finding a two-page book embedding for it. And the assignment of the edges to the two pages is part of the input. This problem lies between other two very important graph drawing problems, clustered planarity and simultaneous embedding with fixed edges, which are very hot topics currently. P2B can be used to solve cluster planarity when there are only two flat clusters, and can be used to solve CFI when the intersection graph is a star. We find it interesting and promising in the way how the book embedding gives a different point of view on these two problems, which are apparently very far from it. Hong and Nagamashi solved P2B with a linear time algorithm, and they characterized the problem as the problem of finding a particular plane embedding of the input graph. Given such an embedding, it is possible to build an auxiliary graph from it. And finally, a special O'Leary tour from this O'Leary graph gives an ordering for the nodes along the spine of the book embedding. Now I will give you a very fast overview of the whole algorithm, so don't worry if you don't get all the details now. Let's say we have a graph, and the algorithm starts searching for an embedding for it. When one is found, the auxiliary graph is built from it. And finally, the O'Leary tool gives the ordering for the nodes. The O'Leary tool must be non-self-intersecting, meaning that it is possible to draw it without crossing the already drawn line. Our contribution to this work is an implementation of the algorithm. However, we performed some modifications to the original algorithm in order to make it more efficient, to improve efficiency. Please note that it's not about asymptotic time complexity, since the algorithm was already linear. We instead lowered the constant factors of the running time. Among the modifications we have done, there is a part of the SPQR3 algorithm which finds an embedding. The part that deals with P nodes that use a brute force approach and code generation. Finally, we add the details to the proof of correctness for that part of the algorithm that searches the O'Leary tour. Now we'll discuss the details of the algorithm. This part is common between our work and the original paper. We search for a plane embedding that is said to be disjunctive and splitter-free. Recalling that the edges are partitioned in two groups, let's call them red and blue, we say that a node in an embedding is disjunctive if all the incident red edges are consecutive. While a splitter is a cycle whose edges all have the same color, where in both the areas of the plane the cycle identifies, there is either a node or an edge of the other color. For example, the first cycle in the picture is not a splitter since it's empty outside. A disjunctive and splitter-free embedding must be found for every biconnected component. And it is done by a dynamic programming algorithm based on SPQR3s, which collect information from the children of each node of the SPQR3. This information is about the presence of colored paths between the poles of each child. However, only those paths that are part of some colored cycle are of interest since they could be a splitter. Please note that we also have information on the parent of the SPQR3 node, and later I will show how it is possible. With this information, it is possible to make embedding decisions. In the figure, there is a virtual edge which has a wrong flip. And this produces a splitter which otherwise would have been avoided. You can see that the colored cycle separates two nodes in the graph. Once this splitter-free embedding has been found, the information is combined and set for the current node. A similar work is done for disjunctiveness. This time, the information collected from children is about the color of the incident edges to the tuples and the ordering of such edges. For example, these edges have only blue edges incident to the poles, while this one has all blue followed by all red. We call such an ordering color pattern. A pair of color patterns is collected for each child. We don't have color patterns for the parent this time, but we know which color are incident to the poles. Again, the information can be used to make embedding decisions. In the picture, there is a virtual edge which, that has a wrong flip, making a node to be not disjunctive, since it has more than 2 color changes in the clockwise ordering of the incident edges. Then finally, the information is combined and set as a pair of color patterns for the current node. Now I will discuss the modifications we have done to the algorithm in order to make it more efficient. As said before, we have information on the parent as well. And this information is about the presence of colored paths in the parent and the colors incident to the poles. This information can be collected by preprocessing the SPQR3. That is a bottom-up traversal of the SPQR3 followed by a top-down traversal which combine the collected information. Another important point is that constraints imposed by disjunctiveness splitters must be considered together, since they could be in contrast. For example, in this figure, there are 2 children whose flips are constrained by disjunctiveness due to these red edges. But unfortunately, this produces a splitter, which is unavoidable, meaning that the instance is negative. That is, there is no book embedding for it. Broadly speaking, we need some information for both the parent and the children. We need to know about the presence of colored paths and the colors of the edges incident to the poles that are color patterns for the children. Everything is combined and used at the same time in order to greedily construct an embedding for an SPQR3 node. The original algorithm doesn't do that. In particular, it doesn't exploit the preprocessing step to collect information on the incident edges. And for this reason, it has to build several embeddings for each SPQR3 node. In particular, all the possible disjunctive embeddings, leaving to the parent selecting one. The algorithm is still linear, since those embeddings that have the same color patterns are equivalent. Our approach, however, produces exactly one embedding per node, being so more efficient. Moreover, by handling all constraints at the same time, we can early detect negative instances. Among the modifications we have done to the algorithm, there is the part of the SPQR3 algorithm that deals with p-nodes. Embedding a p-nodes basically means finding a good permutation for the virtual edges composing the parallel. In this problem, it is possible to group together those edges having uniform color patterns, for example, these 2. Grouping the virtual edges reduces the size of a p-node up to 8 virtual edges. That is, it's limited by a constant. And for this reason, it is possible to use brute force to search for a solution. Basically, the instance can be matched against all possible solutions until one is found. The set of possible solutions is the set of those permutations yielding disjunctive and splitter-free embeddings, and can be generated by an algorithm that starts from the desired result. Let's say that we want a permutation for giving an embedding with a specific pairs of color pattern. It must be noticed that given two color patterns, there are several ways to align them, making them slide on each other in this way. For example, in this slide, we can see 3 different alignments of the same pair of color patterns. Let's concentrate on the first one on the left as an example. This slide shows how an aligned pair of color patterns identifies colored zones where virtual edges with the same color can be placed in order to obtain a permutation with the desired color patterns. And the algorithm that generates the set of solutions simply tries all the combinatorial possibilities of this process. The original algorithm performs a brute force search as well, but it has among all possible permutations, which, although are limited by a constant, they are still quite a lot, since all possible permutation of 8 virtual edges must be tried, and all the possible flips of the virtual edges. We search in a much smaller space, since we only match against good solutions, being so more efficient. Moreover, the set can be batch generated by an offline procedure, making search very fast. Our approach can be generalized in 3 steps. First, the decided properties of the permutations are formalized in a specification. Then, this specification can drive the generation of the set of all solutions, and finally, the instance is matched against all solutions until one is found. Now we'll describe the part of the algorithm that finds the Eulerian tour, giving an ordering for the nodes along the spine of the book embedding. Let's assume that we have a disjunctive and splitter-free embedding for the graph. We construct the auxiliary graph by placing a node in each original face and by placing directed edges in such a way that on each node they separate red edges from blue edges in this way. Please note that although the auxiliary graph recalls the dual graph, it does not, since it also contains original nodes of the graph. The auxiliary graph obtained is Eulerian, and for this reason it can be decomposed in cycles. Being an embedded graph, the cycles are nested, and this hierarchy can be represented by a tree. Visiting the tree of cycles with a DFS visit clearly gives an Eulerian tour, since each edge is visited just once. It can be non-self-intersecting as well. The reason is that on each node, there is an outgoing and the incoming edges are alternate in the clockwise ordering of the node. And by following these alternates, it is possible to avoid intersections. By following this principle, when passing from a father cycle to a child cycle that is nested in it, it is possible to have a tour that is non-self-intersecting. And now I will discuss the implementation of this algorithm. We implemented it in C++ language and used the 2 graph drawing libraries, GDToolkit, which acts as the main framework of our application, and OGDF for its capability to build SPQR trees in linear time. As said before, the p-node embedding part of the algorithm must perform a brute force search. It is fast for a computer, but there are quite many cases for a human programmer. They are 180. And for this reason, we developed a code generator that, given the specification of the good permutations, it generates the C++ code performing the brute force search. And please note that the same algorithm also produces the table in this slide. And now the experimental part. This is the environment we use it, basically a Linux platform with standard C++ language. In order to test for performance, we need a lot of positive instances. And for this reason, we developed the graph generator, actually a solution generator, since it generates book-embedded graphs. The parameters of this generator are the number of nodes and the number of edges. We used the generator to generate 3 sets of instances, which have different edge densities. This is motivated, we did this to have different kinds of SPQR trees. In each set, the graph size ranges from 10,000 to 100,000 of nodes. And each value is averaged among 5 graphs of equal size. Now, a few charts showing the statistics on our graphs. It can be seen that when the edge densities increase, the number of connected components decrease. It is quite obvious. For example, in the last set, we only have tri-connected graphs, since they are basically triangulations. The same things can be seen by SPQR3 point of view, with the last set having graph with only R nodes in their SPQR3s. The result of our experimentation met our expectations, since the application runs linear time with our dataset. To conclude, the results of our work is an implementation of an algorithm to tackle the P2B problem. And we did it by modifying an original algorithm by Ong and Nagamoshi, with modification aimed at increasing the performances. We tackled a part of the SPQR3 algorithm, the part that deals with p-nodes, with a brute force approach, which uses code generation. What's more, in the future, variation of P2B should be investigated because of its relationship with the other problems seen at the beginning. Variations should be investigated in order to try to model more cases of SIFI. We have seen that P2B models the case when the intersection graph is a star, and one could try to generalize this result by modeling the case when there are more than one star, a double star, a caterpillar, or a tree. That is. Thank you for your attention.
Any questions for Marco? Walter?
I'm quite happy that you used the toolkit, but I actually don't understand why you needed 2 libraries. I mean, in a GDF, you have inner time implementation that's SPQR3. Why you actually use it?
Although it's not documented, the GD toolkit implementation of SPQR3 is not very fast. It's not efficient. It's not linear. I think it's something like quadratic or cubic, because when it was developed, it's not aimed to be efficient. However, the rest of GD toolkit, we found it to be quite easy to use, and we were very used to it. So it worked very well as a main framework for our application. and we mixed them together by translating SPQR3s built from GDF to the GD Turkish format.
Yeah, my question is, in this problem which your algorithm solves, you kind of search for this Eulerian tour in the dual of the graph. You search for an embedding such that the dual has this Eulerian.
It's not really the dual graph. It's sort of.
It's sort of, yeah.
Sort of. Okay.
Have you also studied the problem that you don't, because in a Eulerian tour, the start vertex and the end vertex has to be the same.
Yeah.
Have you also studied the similar problem where you don't search for this circle but for a path, because this could be strongly related to double-ended Q layouts, which we have studied recently?
Okay. Actually not, because
Because in this case you can have this, you can allow for these separators, but only for two of them, because the one separator where you start this Eulerian path and not the separator in which you end this Eulerian path.
Yes, but a closed cycle models a book embedding, and it's the only way. You have to start to begin and ends to the same point.
Because with the double-ended Q, you don't have this restriction anymore, and you essentially, because this two-page embedding is also related to these two stack graphs, where you have this Hamiltonian circle in this planar graph. In the double-ended Q, you simply replace this Hamiltonian circle by a Hamiltonian path. And the same happens in a sense with the Eulerian path and a Eulerian circle. When you study, instead of two steps, double-ended Q.
I see. It's something to study further.
Any other questions? Okay, so thanks. Do you have a question?
Can you guess how the problem becomes if you put further constraints on the order of the vertices on the spine? So if you put partial order or something?
Yeah. The original motivation for our work was the relationship between the SIFI problem and this kind of book embedding problem. There is a result from Angelini et al. In 1210, I suppose, showing how the SIFI problem with a connected intersection can be reduced to a SIFI problem with a tree intersection. And this can be reduced to a book embedding problem where the order of the nodes along the spine is constrained by a tree. And that's the reason for this last point. Yeah, it should be investigated.
More questions? Okay, let's thank to Marco again for nice presentation.